Hello everybody. Today we have a interesting mathematical problem actually, because there is no physical system like this. The system is here an infinite charge sheet. So this is goes in infinity in every direction. So this can be thought of as an XY plane. Say, as for example, XY plane, and this is the entire plane. So amount of charge is infinite. It's just the charge density. So the charge density is like Coulomb per meter square, constant throughout. Okay. So this is definitely unphysical because if you just integrate this being constant, integrate infinite area, you're going to get infinite amount of charge, and there is no, you can't have infinite amount of charge. Okay, but we're going to do this problem because we will use it to find solutions to more interesting physical problem like this one. Say you have two metal plates, then if they face each other up, they have opposite charges, they face each other, then and they're not separated by a large distance compared to the size of the plates, then they're kind of like a space between them. They will observe this plate to be very large. Essentially, we can say infinite. So what we'll get here, we can apply it here to get an idea of what the electric field will be at some point P between the plates. You can also get a idea about if you have a metal ball and point P is very close to the surface, what the electric field will be like there. All right. If the point P is inside, over here electric field will be 0 because there's a metal ball, electric field inside 0. Also, the charge is only on the surface, is spherical. We already know inside a spherical shell there is no charge, no electric field. So this one is kind of similar to that. Say all the charges are on the surface, only on the surface, sigma Coulomb over meter square, and you may have a physical cylinder, finite size, but point P is very close to the surface. So what's the electric field? For this also you can apply a result that you got over there. Okay. So this is a very important result. Let's go through the arguments. You can do this, find the electric field here a couple of different ways. So there's two ways. So the two ways to do it. This answer. One is just to integrate. What do I mean by integrate? So we can, because this is going into infinite in a direction, we can do this integration in a so imagine a ring. Imagine a ring, and for this ring is between, say, R, and this distance is dr, this thickness is dr. So this ring has area is 2 pi r dr, right? That's the area, and the surface charge is q, sigma. So this is the charge q, and distance d, you remember that this will a charge from here and a charge from here, opposite charge from there, they will have electric fields pointed, and so horizontal part will cancel out and only vertical part will be there, right? So that's the electric field will be pointed vertically up, right, at that point. And so if you wanted to integrate, you would have this is dq. So you'll have a dq and the distance from this ring will be same for every point of the ring. So you'll have a r square plus d square, and then you'll have a from this point, if this is the angle theta, let's call this so this will be angle phi, so this angle phi, so we have cosine phi we want. So you had so the EZ part will be just cosine phi, and cosine phi will simply be this d over that distance, d over r square plus d square square root. Okay, so this is the DEZ from the ring, and then I just integrate. So EZ at P, so is equal to this, I put down here 2 pi sigma, and then you have r dr, so the r doesn't come out, so r dr, and then d is 2 pi sigma times d comes out, and I have to integrate r dr over r square plus d square 3/2, and to go in every direction I go 0 to infinity in the r variable, and that should solve this problem. And so the E at P will be E at Z, this thing I found, times k hat. So that will be the answer. And if you do it out, I'm not going to do it, but if you do it out, the answer should be sigma over 2 epsilon naught, and the EZ will be this. So if you already see, I just didn't even do the integral, I remember the answer, right? It turns out you can get this answer without doing a whole bunch of integral, by exploiting some of the expectation and identifying appropriate closed surface for Gauss. So from the Gauss's law, this is much easier if I use Gauss's law. So if I have this very large plate, so we already got through over here argument that if any point P, now electric field is pointed that way. So if I go another, so this is say this is the x-axis, and say this is the y-axis. So if I'm going another point over here, same distance d. See, atmosphere can depend on distance d, right? Distance d, another point distance d. This point is no different than that point because this is going into infinite direction, right? So all points, as long as go in this plane at some z equals to d plane, all points should be the same. So electric field, whatever it is, this it has the same magnitude as this, and direction is same. So if I can say, let's take a small area, so area in this z equal d plane. So this area, let's call it area A. So this is a surface, so this is surface S1, and I can find the flux through that, right? but that wouldn't be complete in terms of Gauss's law. I need to have a enclosing surface. So I imagine that I go through this. I take a box which goes equally distance down. So this is in the plane, and then I go down, and I go down same amount. I go down same amount. So this is area A. So I've got now, if you look at it, I got a whole bunch of surfaces. We got this side, and this side, and in the back side, and then we got this surface at the bottom. Let's call it S2, and S3, S4, and the front S5, and the back S6. So I've got 6 surfaces, and so S Gauss equals to S1 plus S2 plus S3 plus S4 plus S5 plus S6. Now, if and in the Gauss's law, if you remember, Gauss's law is on a closed surface S, E dot n hat dA. This integral is equal to how much charge was enclosed. So this will be the charge enclosed, will be thing that's in here, right? The crossing the charge only resides on this area. So this area is inside the box. So charge enclosed over epsilon naught. So if we look at the left side, the right side is very easy. Right side is just going to give me, sigma times area A over epsilon naught. So this is very easy. Now the left side is going to give me on each one of these surfaces. So on S1, if this, I call it E, so E times A, because inside n hat is normal from inside to outside. That's the direction of the normal, right, in this formula. So on S1 I get this thing is just E times n hat is E times is n hat is along the z directions. This is along the z direction. So we're just getting EZ. EZ times EZ times A. On S2 down here, the normal is pointed this way, and electric field is also pointed this way. So this is also going to be EZ times area is going to be the same. And on S3, let's look at this S3. On any point above, if I'm above the plane, the electric field point that way, but the normal is pointed. Let's look at normal. Normal is pointed that way. So normal is pointed to the y direction, but the electric field points z direction. So they so normal is j hat, but electric field is EZ k hat only. So that means this integral equal to 0. So same argument on S4, S5, S6, all these integrals are 0. So these are only 2 integrals. So you got a 2 times EZ times A equals to, this becomes sigma A over epsilon naught. Okay, so the A was arbitrary, cancelled out. So this gives me EZ equal to sigma over 2 epsilon naught. Okay, so so we have a answer to this problem, that if you have a one charge seat, you are going to get an electric field like this. So I'm going to do one of the applications, and I'm not going to do these other applications. Okay. I would say you should memorize this formula. Okay. So okay. Let me because it will come up again and again. All right. Let me erase this and try to do that one of the applications. Okay, so let's do this application. So when suppose I have two metal plates, and I connect this to the positive side of the battery and this to the negative side of the battery. So this will put positive charges and going to pull towards the other plate. so we're going to have a large plate and another large plate. So let's see if this all positive charges, just like I said, this all be negative charge. If they have the same amount, so this one is like a plus sigma, and this will be minus sigma, and they are going to be distance d apart, and they're facing each other parallel. Okay, and so there's a point P. Let's see, this dimension is A and this dimension is B. So P, if this distance from any of the plate, it's like D plus, and this is D minus. Both D plus is much less than A or B, right? D minus or D plus is, so it's as if very so this will behave like, if I just look at the positive plate and have a point D plus from there, point P, for it this this plate will look like as if plate of charge was infinite in size. Okay, so we know the formula for this. So if this is sigma, then if this is plus, then the electric field is pointed this way, so let's call it E plus. And this is actually independent of the distance, because just is the formula is this for one charge like that. Okay, so at point P, and if we do the same thing for this negative charge, so this is negative charge, and point P is here, and you have this is D minus, so this is minus sigma. So now we'll just call it sigma, but this sigma this is less than 0. Okay, let's call it minus sigma minus, let's call it sigma plus, sigma minus. So when we have this charge, electric field will be pointed this way towards this plate, which is going to be same direction as that, because the negative is this, the positive. So negative point was negative plate, positive point also towards away from the positive plate, right? So they are going to add. So E minus, let's call it A minus, is sigma minus over 2 epsilon naught. And we should make it positive because we're already telling the direction. This is already positive. So when I add these two, if this direction is a z-axis direction, then EZ is going to be sigma plus sigma minus, so this absolute values added, over 2 epsilon naught. And if they're equal to each other, so if they're equal, then it's just going to be if sigma plus equal to sigma minus equal to sigma. So this is a very famous result. You can see the other formula had sigma over 2 epsilon naught, and because the superposition from the two plates, this formula has sigma over epsilon naught. And there's a lot of confusion. A lot of students just memorize the formulas and then don't remember that here we have a superposition of two problems, okay, two charges. Then they get into trouble. Okay, let's do, if you just had one metal plate, what will happen? Okay, that's another problem that comes up. Okay, so this is a kind of tricky problem. This also what the electric field will be is an application of what we just did, but in an interesting way. So if I place plus q of charge, and the area dimensions for the plates are that, and say the d is much less than a or b, so that the plate looks infinite from the perspective of this point P. Okay, so you'll have and maybe C is small, you know, C is also it doesn't matter what C is actually, but let's C is small. C is small compared to AB, so it's a thin plate. So when I place the charge, most of the charges will be along this, right? And there will be some charges on this faces, some charge on this faces, bottom and back, and then there will be some charges on that face. So this amount of charge, this is the, so let's call it front face and the back face. So they will have the charges. So the sigma will be actually charge Q will be distributed over all the things. You can say 2 times AB plus 2 times BC plus 2 times AC, and because C I'm going to assume to be small, we can say this is ignore. So that's going to be sigma. Another thing that should notice is electric field in the space between inside metal, electric field inside metal, when charges are not moving, when static charges, which is the case here, is actually 0. This is one of the properties of metals, okay, that defines what a metal is. Metal have a lot of charges which are very easy to move, and if they're not moving, which means electric field has to be 0, because if there's any electric field, then those charges will find force on them, and so even if they're not moving at t equal to 0, they will start to move immediately after that. Okay, so if we got sigma is this, so you would think that there are two sheets of charges, right? You think there's zero charge here and zero charge here, but because there's electric field equal to 0 here, space, you over here, you should, how should you add up? Okay, that's a question. So it's like a, if I have a plate here, and if I had a plate of charge here, and each one was producing an electric field over here. So and they are on the both sides. So this one is producing electric field, and this one is producing electric, let's call it a front and back. So electric field from front and electric field from back, and so electric field will be electric field front plus electric field back. And so, and they're all, this is the z direction, so this is a z, and this is z, this is z, and all of them positive. So you have a sigma over 2 epsilon naught plus sigma over 2 epsilon naught added up sigma over epsilon naught. And so this q over 2 ab epsilon naught. So okay, we are we're not going to do these other ones. If you want to do it, they're very nice exercises for you. I will stop here. The video is already very long. Talk to you later. Bye.